We are Group 18 and we are developing the Portable Unitary Throwable Target Interceptor, also known as the P.U.T.I. Our team is comprised of 4 individuals. We have Alex Everson, who is an electrical engineering student. You have me, Callum Fuller, who's an electrical engineering student. Nathan Kimmel, who's also an electrical engineering student. And Jake Tattersall, who is a computer engineering student.
From early fortifications to the development of missile defense systems, humans and the societies that reside within them have always designed and built protection technologies to protect themselves from outside threats. In today's day and age, war makes use of small drones, UAVs, and other improvised aerial projectiles. These hazards pose threats to not only soldiers on the front lines, but also to civilian infrastructure, where defenses such as missiles are too costly, or rifles which are too impractical to hit and stop your target. Active defense technology has seen major processes in recent decades from large-scale missile interceptors to vehicle-mounted active protection systems, yet these solutions remain inaccessible outside of military use due to their high costs, large footprints, and complexity. This makes a gap for smaller, more adaptable systems that can quickly respond to threats.
This leads us to our basic goals and objectives for the project. Our first basic goal would be to create a compact defense system capable of detecting and targeting stationary targets. This would be done by using cameras and microwave sensors in combination to detect objects in the field of vision, as well as using an SPC to control the camera and to communicate with the microcontroller to move the motors and lasers. Our next goal would be to allow the device to be quickly deployed and moved, and this is done by using 3D printing to create a shell for the components of the device to be placed in, as well as a buzzer to notify the user of successful targeting. And finally, our last goal would be to cover a significant target space in near ideal route conditions, which will be done and tested by seeing if it can cover a 120-degree horizontal field of vision and at least a 60-degree vertical field of vision. We now move on to the advanced and stretch goals and objectives for our project. Our first advanced goal will be to target and track low velocity projectiles with predictable trajectories, which will be done by using the SPC and microwave sensors to detect faster moving objects with a latency of less than 100 milliseconds. Our next stretch goal will be to make the device fully weather resistant to harsh conditions, including sandstorms, rain, and snow as examples. This will be done by using aluminum to create the shell of the device for increased durability while staying low weight. Another goal would be to allow the device to attach to different faces such as walls and ceilings, which would be done by adding suction cups to the base of the device while still allowing for the device to be deployed in less than 1 minute. And finally, our last stretch goal would be to detect and disable a small drone and detect humans to avoid accidental friendly fire, which would be done by using a small projectile powered by pressurized gas to hit the projectile. From those goals and objectives, we came up with our engineering specifications. Of those, the 3 most important are the targeting response time, which needs to be under 500 milliseconds, meaning upon seeing an object detected by the camera, the P.U.T.I should react to it, and hand-to-hand with those go with range and target size, showing proof of concept, being 1 to 5 feet for the range and 6 to 12 inches for the target size. For the actual target itself, we went with a green playground ball that demonstrates that the P.U.T.I can be trained to see concepts rather than specific colors or shapes. Additionally, since we had different size balls, both should be detected by the P.U.T.I as they are the same concept.
In addition to having an MCU, the project required a single-board computer capable of performing real-time image processing. Initially, ideas like the Raspberry Pi came into mind, however the choice of the SPC would be determined by the image processing method. If the method chosen was resource demanding or would benefit from a GPU, then a more powerful board would be needed. In the end, a computationally heavy method was required, so the NVIDIA Jetson Aura Nano was selected. The Aura Nano was advertised to perform well with computer vision models and could allow us to select a more accurate computer vision model thanks to its GPU. The camera is the method of which the SPC will capture images to do image processing. The camera should have a wide field of vision and be capable of hitting high frames per second. With the Aura Nano having both USB and CSI camera slots, a decision was first made between the 2 options. CSI is a popular interface for embedded cameras and imaging, and has the capabilities of outperforming a USB camera, while using a much smaller ribbon cable compared to a longer USB cable. While the CSI cameras were typically cheaper and could bring better quality, users on the NVIDIA forums noted problems in getting these CSI cameras to function, even though they were advertised as supported. The camera chosen was the ELP OG05B10. Although it was priced higher, it featured a global shutter, meaning reduced motion blur, which would significantly help with object detection at high speeds. It also had incredible resolution and frames per second. The detection framework for detecting our targets is a key part of this project and heavily influenced the SBC selection. OpenCV will be used in the project to access the camera and perform other tasks, but will not be the primary detection framework. Instead, a YOLO model from Ultralytics will be used. The YOLO model is unique in that it performs only a single pass over the image to search for objects, so it will provide the real-time detection speeds necessary while providing a high level of accuracy. The YOLO model used will be custom trained using the camera chosen.
The laser is an incredibly important component of the P.U.T.I, as it will follow the target throughout the air, ensuring proper detection and targeting occurs. In a real-world practical case, a much higher powered laser would be more preferred and used as it would have the actual capabilities to disable or completely destroy the targets. However, due to the safety concerns with this and the huge costs, we opted to use a much lower powered laser. Out of all the laser diodes we considered, we ended up choosing the 1054 laser diode by Adafruit. This laser diode is within the red wavelength that we wanted, having a wavelength of 650 nanometers. It also accepts an input voltage of either 3.3 volts or 5 volts, meaning it's easily incorporated into the PCB, and the power of the device is very small, having a power rating of only 5 milliwatts. This means that the laser diode is only considered a Class 3A laser, so eye protection is not required when operating the laser. Additionally, the small packaging of the laser means it will be compact and easy to fit into the CAD of the device. The I2C multiplexer is required for the P.U.T.I, since all of the radars will use the same I2C channel. However, the ESP32 only has a limited number of channels. The multiplexer will then allow us to use all the components that communicate via I2C working when we need them to. The I2C multiplexer that we decided upon was the TCA9548APWR. We wanted a multiplex that had at least 2 channels and took 3.3 volts or 5.0 volts. Even though the TCA954APWR has many more channels at 8, we thought it was worth the additional expense, in case any of the channels had issues or we wanted to have additional components. Whilst the 74HC151D multiplexer is very similar, the key differences between why we didn't choose this multiplexer and why we chose the other multiplexer is because it's an incredibly small footprint size, making it difficult to solder, and the very low current, which would limit the size of the pull-up resistors we could attach to the I2C lines. The humidity sensor will be used to measure the relative humidity of the surrounding environment, as well as the ambient temperature. Collecting this data is particularly useful to the microwave sensor modules, as they are the component on the board that are most susceptible in regards to electrostatic discharge. They are also the most exposed components, so we want to make sure the outside environment is not too hot. We compared 5 different sensors based on their humidity range they can detect, the type of output they produce, the response time, and the voltage supply required to power the sensor. Based on all of these factors, we decided to go with the AM2320 by Adafruit. This sensor operates at the correct voltage supply, has a range large enough to encapsulate all environments the device could possibly be deployed in, has a relatively short response time, and outputs the values via I2C, making it easy to use. Additionally, as mentioned before, we also want to use this device to measure the ambient temperature, which the AM2320 is perfectly capable of doing.
For the microwave sensor subsystem, we evaluated multiple 60 GHz microwave sensing options, including the A121 Bayer radar chip, 2 Texas Instruments millimeter wave solutions, and the Akinir XM125 module. Key comparison factors included operating frequency, communication interface, onboard processing capability, range, resolution, and field of view. While the A121 offered flexibility, it required external RF layout and significant signal processing, which would create significantly more computing load by the main controller. The TI solutions provided powerful integrated processing, but were too powerful for the scope of the project and did not have all data needed in the documentation. We ultimately selected the Akinir XM125 module because it provides onboard processing, has multiple sleep modes for power efficiency, and wide viewing angles. Additionally, having an integrated MCU significantly reduces any RF design risk and integration complexity while still meeting all other requirements. For choosing an LCD, we compared 4 options. The first was a 5-volt LCD by New Haven with a current draw of 1 milliamp and a price of $7.45. It uses parallel wiring, meaning 11 pins would be needed for programming. The second was a 5-volt LCD by Sunfounder with a price of $8.95. It uses I2C for communication, which, while more pin efficient than parallel wiring, may add more stress to the I2C lines, which already support 3 radar modules and the humidity sensor. The third is a 5-volt LCD by Orient Display, which draws 1.2 milliamps and costs $11.21. It uses SPI for communication, which is more pin efficient than parallel wiring and will not affect other devices since nothing else uses SPI, unlike the I2C. The fourth is a New Haven LCD very similar to the first, but runs at 3.3 volts, is more expensive, and has higher current draw. Due to its previously mentioned communication efficiency, the 5-volt Orient Display LCD was chosen. Since it does run on 5 volts and the ESP32 runs on 3.3 volts, a simple 4-buffer gate one-way level shifter must also be used for LCD communication.
The PuTTI requires multiple voltage regulators to supply consistent power to the various different peripherals that we have on the board. While there are some inexpensive and adjustable regulators, because they're high frequency, they introduce a lot of switching noise and EMI effects which can negatively impact our peripherals. With this in mind, we decided to go with the LM2679S 3.3/5, as it will simplify PCB layout and overall improve the system stability. Additionally, the voltages don't need to be adjustable as they will be receiving a constant stream of 3.3 and 5 volts respectively.
For our project, the Ovionic Air is the most affordable out of all the batteries, while still giving us more than enough power for our project. The weight and size are also a huge factor concern for the internals of the PuTTI, as the SBC and PCB take up a decent bit of space, so having a small, lightweight battery is super ideal. While its capacity may be less than that of the other batteries, this is made up for by the fact that we can get multiple batteries for a project instead and just swap them out when need be.
For our servo, we went with the Endura. Although it may be bulkier than the other two servos, the Endura more than makes up for that fact with its cost, torque, and speed, which makes it an easy pick. In addition to it being superior in terms of strength, it also has the added upside of being completely waterproof, which could be a big deal if the PuTTI were to be ever deployed outdoors. If you look past the numbers in the table below, the Endura stands out for its overall reliability and build quality as it's designed to handle stress without sacrificing precision. Its brushless design gives a smoother motion over long periods of use. This combination of power, durability, and affordability makes the Endura not just the most practical choice on paper, but also the most dependable option for consistent performance in real-world conditions.
This is a visualization of the device. We have a rendering of the device that was made using Fusion 360. And then we have the complete PuTTI device once all of the components that have just been listed off were put together into the CAD and fully assembled. The hardware block diagram outlines the responsibilities for each team member and shows how the power is distributed to each component and how each of the devices and peripherals interact with one another. The LCD, both the pan servo and tilt servo, the laser and level shifter will be powered by the 5-volt regulator. The buzzer, ESP32, humidity/temperature sensor, and I2C multiplexer are powered by the 3.3 volt regulator. The microwave sensor modules operate from the 1.8 volt regulator, while the single board computer is powered by the 19 volt regulator. Additionally, the SBC will power the camera through the USB port. We will have 2 power supplies with a 4S LiPo battery providing power to most of the board, connecting to the 1.8 volt, 3.3 volt, and 5.0 volt regulator, whilst an 8S LiPo will connect to the 19 volt regulator. Knowing how each of the components communicates is also important. The humidity/temperature sensor, along with the microwave sensor modules, communicates with the ESP32 using I2C via the I2C multiplexer. The LCD communicates to the ESP32 over SPI. The motors are controlled using pulse width modulation signals. The SBC and microcontroller exchange data through U.A.R.T, and the laser and buzzer are controlled through simple GPIO outputs. Understanding how much power we will be using is incredibly important to understanding how long the device will be able to function for. Here we have the maximum power that each component can produce, listed in a power table. The largest consumers of power are the single-board computer, having a maximum power usage of 45 watts, the servos, which both have maximum power usage of 25 watts each, the camera, which has a maximum power usage of 1.15 watts, and the microcontroller, which has a maximum power usage of 1.2 watts.
This is the general software flowchart diagram. To go into more detail on it, the device is first turned on. The SBC and MCU then perform a handshake with each other to verify that communication is online, and of course to verify that the environment is okay. The SBC then loads the YOLO model and begins using the camera to search for targets around the field of vision. When a target is detected, the MCU is signaled with predicted pan and tilt values that the laser should turn to. The MCU uses these values to align the laser using the motors, while the microwave sensors adjust as needed. While this happens, the laser is turned on and the buzzer is activated to announce that a target has been identified. While the target is in frame and there is a current target, the laser and buzzer will continue to move and sound. And once finished, the device will start over. This is the software flowchart for the SBC. The SBC first connects to the camera and loads the YOLO model. During this, an undistortion algorithm is enabled to ensure that calculated angles and locations when a target is detected are appropriate. This is because the camera does have some distortion to it. For example, objects near the outside of the frame can appear much larger than anticipated, or they might be in the wrong X and Y location. So the algorithm is based off of predetermined constants used from the parameters of the camera itself. The algorithm then searches for targets. Once a target is detected after a predetermined minimum number of times, it is considered a valid target, and while this target is in frame, the predicted pan and tilt values are sent to the MCU, and this continues while the current target is in frame.
Our radar software architecture is built around the XM125 module, which integrates the Akinir A121 radar chip and an internal MCU, which in the case of this module is the STM32. The process begins when the ESP32 sends a wake-up signal to the requested radar module. The STM32 initializes the onboard A121 via SPI and starts the radar sweep. Measurements from the A121 are captured by the STM32, which initiates the sparse IQ service that returns amplitude and phase, to then organize the sweeps into frames. These frames are then processed using fast Fourier transform and Doppler analysis to extract velocity, distance, and direction information. Once processed, this data is sent over I2C back to the ESP32, completing the cycle. Most of this functionality is already supported by Akinir's software libraries, so our focus is not on designing all this from scratch, but rather on testing, tuning, and integrating the modules into the larger system. Our ESP32 firmware is designed to manage both environmental monitoring and projectile tracking while maintaining low power operation. After initialization of all components, namely the radar modules and SBC camera system, the ESP32 enters low power mode. From there, the software splits into two main routines. First, periodic wake-ups acquire temperature and humidity readings. If these values are within operational limits, the data is displayed on the LCD. If not, a warning is shown and the system prepares to safely shut down. Second, when the Aura Nano detects an object, it interrupts the ESP32 over UART, waking it from low power mode. The ESP32 uses the angle data to determine the relevant radar sector, then activates the buzzer and specified radar. If no projectile is detected, the system disables the radar, laser, and buzzer and resets the motors to starting position. If a projectile is detected, radar data is smoothed, the trajectory is calculated, and motors are updated to track it while the laser is activated. The loop continues until the projectile is no longer detected.
For the device. We have the 3.3 volt and the 5.0 volt regulators. Both of these regulators are very similar, except from some minor changes in the values of some capacitors. As a result, they have the same switching frequency, efficiency, and output current at 256 kHz, 92%, and 5 amps respectively. The 3.3 volt regulator supplies power to the microcontroller, buzzer, humidity/temperature sensor, and I2C multiplexer, whilst the 5.0 volt regulator supplies both pan and tilt servos, the LCD, laser, and level shifter. The other two regulators for the P.U.T.I are required to power very specific components. The 1.8 volt regulator is a low dropout regulator that has a 1 amp output current and is required to power the 3 microwave sensor modules. We were able to use an LDO since the voltage is very small and the load of the regulators would also be quite low. The 19 volt regulator is the same regulator base as the 3.3 volt and 5.0 volt regulators. However, the footprint is quite different to accommodate for the much larger output voltage that is required. It once again has a switching frequency of 256 kHz, operates at around 92% efficiency, and has a maximum output current of 5 amps. This regulator only powers the single board computer, and due to the large output voltage, will have its own battery supply and switch. These are some of the peripheral schematics. We have the humidity/temperature sensor that has 4.7 kilo ohm pull-up resistors and will have a header to ensure the sensor is able to measure the ambient temperature rather than the internal temperature of the device. We also have the laser schematic, which utilizes a MOSFET. This helps to increase the efficiency and reduce heat from excess current. It would also allow for pulse width modulation in a higher powered laser that would allow for the laser's power to be changed and dimmed, but since we're using a lower powered laser, it's mostly a safety consideration to ensure huge amounts of current don't go through the device and damage the laser or other components on the board. Some other peripherals are on this slide. We have the buzzer, which is controlled by an NPN BJT, which amplifies the current from the microcontroller's GPIO pin. It also has a flyback diode. Since we're using a magnetic buzzer, we don't want the transistor to be damaged in the case of a voltage spike, which could also then damage other components. We also have the LCD, which is connected to the level shifter that steps up the 3.3 volts from the MCU up to 5 volts to power the LCD, and contains a potentiometer to control the contrast of the LCD. There are some additional schematics, however these are mostly headers which just connect components such as the pan servo and tilt servo, as well as the UART connection to write code to the ESP32. There is also the radar board, however Nathan will talk about those next.
Our radar PCB is a 1.5 by 1.5 inch 2-layer design supporting the XM125 microwave sensing module. It provides a dedicated 1.8 volt rail and a 3.3 volt rail, each with decoupling capacitors to ensure a stable power supply. A boot switch is connected to the radar module's boot 0 pin with an external pull-down resistor, allowing us to update the software. The board includes 3 6-pin headers. While only about half of the pins have planned uses, the others are routed for any potential future functionality. To minimize the profile, most components, aside from the radar module and capacitors, are located on the back of the PCB. This allows the radar module to sit flush with the 3D printed chassis wall for a compact, clean installation that maximizes the field of view outwards. The PCB also includes mounting holes, but final testing will determine whether metal screws affect how efficient the radar is.
Here on the left, we have the schematic for the MCU, which also shows the mux needed to provide the multiple I2C bus lines needed for the radar modules and humidity sensor, and the schematic also has the pinout for our UART, which is used to transfer code to the board. Below that, we have our final main PCB board, which houses our MCU, voltage regulators, and the peripherals for this project. The board consists of 2 layers, with the top layer connecting components, and the bottom layer being the ground plane as well as the jump traces that would otherwise intersect. All regulators were connected with male connecting pins for ease of testing and debugging our board, and all peripherals were soldered to wires which connected directly to the board. Some changes that were made in the final iteration of the board include adding vias along the power rails for ease of testing continuity and power, a level shifter which allowed the 3.3 from the MCU to be stepped up to 5 volts, as well as LEDs giving visual confirmation that the board is being powered on the respective rails.
The voltage regulators were designed as separate PCBs rather than being integrated onto the main board, as this helps isolate the power electronics from the ESP32 and sensing circuitry, which further helps reduce electrical noise and improves overall system stability. This modular approach also makes the system easier to troubleshoot, replace, and scale if power requirements change.
We set ourselves a budget of $1,000 and managed to stay well below that budget by just under $267. The largest expenses were the NVIDIA Aura Nano at $249.99, the ELP OG05B10 camera at $163, and the miscellaneous PCB parts such as capacitors, resistors, inductors, etc. at $109.68. Overall, we ended up spending $733.47 throughout the development and implementation of the P.U.T.I.
During the prototyping and testing phase, we focused on validating each subsystem individually before moving into full integration. We first tested the YOLO Vision model on the single-board computer to confirm reliable object detection for both stationary and moving targets. Once this was stable, we established UART communication between the SBC and the ESP32 to transmit target detection data and position information. Next, we breadboarded the laser, buzzer, and pan tilt motor system using the ESP32 to verify that the motors responded correctly to camera-based target inputs and could accurately aim the laser. We also tested the main communication protocols used throughout the system, including UART, SPI, and I2C, to ensure that they would reliably exchange data. We also implemented and tested the I2C multiplexer to support multiple radar modules and the humidity sensor. During early testing, we experienced a hardware issue that damaged one of the prototype boards. We shorted it. Following this, we became a lot more careful with loose wires and improved our installation practices using heat shrink and ensuring that connections were much more secure. Through continued testing, we found that while the radar modules were functional, the response time and accuracy were not sufficient for reliable tracking compared to the camera system. So we repurposed the radars for close-range safety detection, where they trigger a buzzer and system shutdown when an object approaches too closely, specifically laser shutdown. Finally, all subsystems were fully integrated on the custom PCB and mounted to the 3D printed structure.
In order to test the YOLO model, a dataset was manually collected and labeled. The dataset consisted of approximately 2,500 images, both positive and negative, and these were used to train the green playground balls. Both of the playground balls used were considered the same class to generalize the idea of the green playground ball rather than specifically identify that specific brand and model and size. As you can see from the confusion matrix, there is a very high success rate with the training, 377 true positives, 2 false positives, and 2 false negatives. And in all 4 of those false cases, they were reasonable assumptions to be false. When looking at the images themselves, it is understandable to know why that the model failed to detect them. So in the 377 true positive cases, that is still a very high success rate. The model has shown, very good behavior, as you can see in the image in the bottom left. The ball, this is one example of the ball being detected, and this is with 90% confidence. So the YOLO training has been extremely successful both in testing and in use. The Orano itself is going to be using a Docker container to automate deployment because of the restart capabilities on startup. The Docker container itself is able to access all necessary components such as UART, the GPU, and the camera. The container itself is built on an image provided by Ultralytics, which contains all of the necessary dependencies needed to run our script. All of this combined was meant to help ease with deployment and testing. And after further testing, we see that the container, when running, is able to maintain somewhere between 20 and 30 frames per second, which is extremely reasonable considering that the runtime of the YOLO model is approximately 40 milliseconds. So this is extremely good.
This is the work distribution between all 4 of our group members for the project that we've been sticking to throughout Scene Design 1 and Scene Design 2.